Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today we will learn about double cosets. What are double cosets? First we need to know what is coset. If let me say that a G is a group 1, 3, 5 and 7. Okay, and we take its subgroup H is equal to, this is a group of modulo 8 with respect to multiplication, and we take its subgroup 1 3. Okay, and we take elements of G and multiply by this from left side. This will be left coset. For example, A multiplied by 1, 1 is an entry element. 1 multiplied by 3, it's 3. And for example, 5 multiplied by 3 is 5. And 5 multiplied by 3, 5 3s are 15. And when because it is set of modulo 8, when we divide 8 by 15, this gives us 7. So this is first coset, left coset, and this is second coset. Always the addition of cosets make complete G, the partition of G, and the all cosets are distinct, their intersection is phi. All left and cosets, right cosets. When we multiply this 3 from right side, this will be the right coset. So the union of cosets will make complete G, and intersection of cosets will be phi. Now let's talk about double cosets. What are double cosets? Let H and K be two subgroups of G and A be an arbitrary element of G. Then the set HAK, where H belongs to group H and small k is the element of subgroup K. This type of elements will be the double cosets and is called the double cosets of G modulo HK, determined by A. Every element there will be the different coset, double cosets, and collection of all their cosets will make G complete, and their intersection will be phi. Let's start a theorem related to this. Let H and K be two subgroups of G, then the collection sigma of all double cosets HAK, where A belongs to G, is a partition of G. Partition of G means their union will give complete elements of G, and their intersection will be equal to phi. So let H and K be two subgroups of a group G, and sigma be the collection of all double cosets of HAK. Here is HAK, where A belongs to G. We have to show that sigma is defined partition of G. Partition of G means this is the union of A belongs to G. All HAK will make complete G, and HAK intersection HBK will be equal to phi, means these are distinct cosets. There is no single element will be in both cosets same. So first we will prove the union of HAK, where A belongs to G, will make the partition of G will be equal to G, and Here we can easily see that the first element of this HAK, by taking the identity element from GLA, by taking element A from G, and by taking identity element from H and identity element from K, it will be equal to A itself. And let A belongs to HAK. Similarly, all A means all the elements of G belongs to H union of HAK, because H and K are the subgroup of G. So all the elements in H and K are the elements of G, and we will take the double coset when we take a single element from G and multiply all the elements of H with left side and K with right side. It will surely give us the elements of H union K. It means that all the elements of G are contained in H AK. All the union of H AK, all the union means that uh, H1, H2, or you may say that H1 A K1 and H2 A K2, similarly H3 A K3. All these type of elements, union of all these type of conjugates, conjugates, double cosets make the complete G. Therefore, all the elements of G will contain a union of HAK, but we know that because these are the subgroup of G, so all these elements which are present in HAK, union of HAK, will also contain in G. From 1 and 2 we prove that union of all A belongs to G, HAK will be equal to complete G. They make complete G. Now we are going to the second proof, that HAK intersection HBK will be equal to phi. Now we will prove that HAK intersection HBK equal to phi. Let HAK and HBK are distinct double cosets. These are distinct double cosets. There is no element, single element is present in both cosets. Suppose that, let me suppose we are supposing something, that X is an element which is present in HAK and also in HBK, and intersection of HAK and HBK is not equal to phi, that is equal to X. It means that X is also belongs to HAK and X is also belongs to HBK. Both double cosets X will belong. So the elements of HAK are H1 AK1 and elements of HBK will be H2 BK2. This means that this X in this will be looks like H1 AK1, and this X in this HBK will be looks like this H2 BK2. Let's start. Let's prove. Here I need your attention, please. H1 and H2 belongs to H are the elements of H, and K1 and K2 are the elements of K, and A and B belongs to G. Now we are taking separate their double cosets. H1 AK1 is equal to H2 BK2. This belongs to HBK, and this belongs to HAK. K, H-A-K. So H1 on this side will become inverse and K1 on this side will become inverse. So A is equal to H1 inverse, H2, B, K2 and K1 inverse. Let we take an element Y which belongs to, here I need your attention. Look at this very carefully. Y belongs to HAK. We take Y is equal to H3AK because the element of HAK will be like this, H3AK3. So now put the value of this A here. Put the value of this A here and the value of A is this. So Y is equal to this H3 and this is complete value here and this K3 will be this K3 is here. So let me say that Y is equal to this complete thing is H4 and this complete thing is H4 and K4. And what we see here? We see here that Y is equal to H4BK4. It means this becomes the element of HBK. But Y was the element of HAK. It means that, once again I am repeating this point, here we have proved that Y is equal to H4BK means that these type of elements are in HBK because B is present in center. But we suppose that Y is equal to Y belongs to HAK. Y is the element of HAK. And here we conclude that Y belongs to H4BK4 means that Y belongs to HBK. It means that Y belongs to HBK. It means that HAK is contained in HBK or HBK contained in HAK. It means that HAK is equal to HBK. Here we have proved that these two double cosets are same. So our contradiction, this is the contradiction to our position. Hence HAK and HBK are distinct and HAK intersection HBK is equal to phi. Therefore the double cosets of G modulo HK define the partition of G. Here we have the complexes in a group. An arbitrary subset X of group G is called complex. In G, for two complexes X and Y in G, we define their product as complex XY given by XY. X belongs to X and Y belongs to Y. It was a single definition I have put here. So here we have completed our proof. I hope you understood.